Okay folks, so if you can give it a heading on your paperwork somewhere, angular velocity and frequency. That's angular velocity and frequency. Angular spelling A-N-G-U-L-A-R. Angular velocity and frequency. Whilst you're writing that heading down, you should know and be aware of from your school days probably by now, that in SI units, that's SI units, SI, angles aren't measured in degrees anymore, but they are measured in, Alex, if Alex said radians, Alex is correct. Therefore we'll put a note on that's suitable. In SI units, angles are measured in radians rather than degrees. Jack Glenn, if you're there, read out from the board very, very quickly what you've written down. If Jack isn't there, we'll have Joe. Joe isn't there, Ben. Superb. In SI units, angles are measured in radians rather than degrees. Give you a minute just to take that note down. Very, very similarly then, in SI units also, angular velocity, angular what? Velocity, excellent. Angular velocity is measured in radians per second as opposed to revolutions per second. Therefore, we'll put a note that's appropriate. Angular velocity is measured in radians per second rather than revolutions per second. Josh Lynch, if you can read out both bullet points, if you are there. If not, Josh Tulip. Bullet point number 1, bullet point number 2. Okay, excellent. Bullet point number 1, in SI units, angles are measured in radians rather than degrees. Bullet point number 2, angular velocity is measured in radians per second rather than revolutions per second. Okay, let's see what else we got. There is a symbol that represents angular velocity, and it is this symbol that you can see on the board like so. I'll highlight that in a circle for you. We'll draw it a little bit bigger very, very quickly. Yes, it might look a bit rude, but there you go. That's the way it is. Angular velocity. It's the small Greek omega. Just clear that. You should have that by now. Okay, let's see what else we got. I'll go back for the purpose of your notes if you haven't got them down. The very, very last bullet point. The symbol for angular velocity is the lowercase Greek omega, which is that funny symbol that you can see as such. Lowercase Greek omega. Angular velocity. Okay, let's move on. If you can give a heading very, very quickly, radians or radian in your work. And we'll pick a few people at random. Ali, what's a radian? Define it. If Ali doesn't know, we'll have James O'Brien. If James O'Brien isn't there, Rob Davis. The radian, define the radian. Alex, what's it at? The radian. Okay, let's discuss it. A radian, and you'll probably be aware of it, and you should know it by now, is an angle subtended at the centre of a circle by an arc on the circumference which has length equal to the radius. Dead easy. If not, I'll put a note up on the board there for you. A radian is the angle subtended at the centre of a circle by an arc on the circumference, which has length equal to the radius of the circle. Give me a minute to take that note down. I'll read it once more for the purpose of your notes. A radian is the angle subtended, S-U-B-T-E-N-D-E-D, at the centre of a circle. A radian is the angle subtended at the centre of a circle by an arc on the circumference which has length equal to the radius of the circle. Might not be very clear to you now, but we will try and clarify that explanation in a moment. Okay, let's move on very, very quickly. Let's see what we got. Since the circumference equals 2 pi r, which is what we need to calculate the area of a circle, and you're very, very familiar with that formula, I take it already, then there must be 2 pi such arcs in the circumference of a circle. I'll read that bullet point out for you very, very quickly for the purpose of your notes. They are just notes for now. We will expand on that theory in a moment. Since the circumference equals 2 pi r, then there must be 2 pi such arcs in the circumference. Since the circumference equals 2 pi r, then there must be 2 pi such arcs in the circumference. Okay, I have a feeling there is another one for you at the bottom there. Hence, there are 2 pi radians in one circle, i.e. 2 pi rad equals 360 degrees. Hence, there are 2 pi radians in one circle, i.e. 2 pi rad equals 360 degrees. Okay, if you're ready to move on, we can progress. Okay, first of all, if you like to draw a circle like that somewhere in your workbooks, as neat as possible, do so now. Alright, shouldn't take you very long to draw that, so we'll discuss. At the centre, I will use a green colour pen. Draw a dot somewhere around about the centre, like so. Well, you all know what the radius of the circle is, and that can be represented by drawing a line, it doesn't matter where it is for now, in that direction, since we are describing the radian first. Do so in your diagrams. Well, the statement which refers to a radian states what? Let's have Joe Creed. If you can read out the definition of a radian, if you're there, that is. If not, we'll have Josh Tully. Okay, yes, the radian is an angle subtended at the centre of a circle by an arc on the circumference which has length equal to the radius of the circle. In other words, for an angle to be subtended at the centre of a circle, we need not just one radius, but we'll say we need another one like so. And you can see therefore that now there is an angle subtended at the centre of our circle by an arc on the circumference. Well, the angle, well, we'll put an X in there for now. We do need a value for the angle, but not just yet. We'll come back to that in a moment. We'll call that angle X at this moment in time. However, what you do need to be aware of is what the radian is defined as. Well, there's the angle at the centre of the circle, subtended by an arc on the circumference. We'll highlight the arc with a dash there and maybe a dash there, like so. Well, we know from the statement or the definition of a radian that that arc length there between the two red dashes should be the same length as the radius of the circle, meaning that that distance from there to there should be such that it's the same distance from that point there to that point there. Makes sense, doesn't it? Revisit your statement and check if it fits that description that you can see on the board at the minute. Hopefully the arc length, or the length of the arc on the circumference from that point to that point there at the top between the two arrows and the two dashes therefore should equal that length from the circumference to the radius of the circle. Okay, I'm going to get rid of the red bits if I can, very, very quickly, if it will allow me to. Okay.